Hello everyone, this is Ryan, your physics teacher. In this video, I'm going to teach you how to multiply vectors. When two vectors are multiplied, there are two possible products, a scalar product or a vector product. In this video, we're going to look at them one by one. The first product that we will discuss is called scalar product or dot product. It is called dot product for a reason that you will know later on. So when two vectors are multiplied and the resulting product is a scalar quantity, that is called a scalar product. On the other hand, it is possible to multiply two vectors and the resulting product is another vector. So that is the case of vector product. Vector product is also known as cross product, again for a reason that you will know later. In this video, we're going to discuss scalar product first. We will give examples, and then later on, we will tackle vector product. A scalar product is represented by the following: A dot B. That is why scalar product is also known as the dot product. Let us first discuss the geometric interpretation of the dot product. Suppose we multiply vectors A and B. This is vector A, and you have another vector directed horizontally. Let us plot them in a two-dimensional Cartesian plane. This one is vector A. The other one is vector B. The angle between them is theta. So vector A has a component that can be projected in the direction of vector B. So this is the component that is parallel to vector B. In this case, this component is A times cosine theta. By definition, in a scalar product, we simply multiply the components of the vectors that are parallel to each other. So for this case, the component of A that is parallel to B is A cosine theta. So we just multiply that to the magnitude of B. So the result is AB cosine theta. This is the magnitude of the dot product. So take note that the dot product is a scalar quantity. There is no associated direction to it. And in this equation, I simply omitted the arrow on top of letters A and B to denote the magnitudes of vectors A and B. Let us consider different cases. So when data is equal to 0, that is the case when the two vectors are parallel to each other as shown in this figure. The value of cosine 0 is equal to 1. Therefore, A dot B is simply equal to the product of their magnitudes. On the other hand, when theta is equal to 90 degrees, you know that cosine 90 degrees is equal to 0. So this is a case when the two vectors are perpendicular to each other. So the dot product of the two vectors is equal to 0. When the product of two vectors is equal to 0, we say that they are orthogonal or perpendicular to each other. For example, find the scalar or dot products of unit vectors. So let us recall that unit vectors are I, j, k. These unit vectors point to the directions of positive x, y, and z respectively, and their magnitudes are equal to 1. I will show in this diagram the directions of I hat, j hat, and k hat. Take note once again that the magnitude of unit vectors is equal to 1. and the directions of these unit vectors are mutually perpendicular to each other. So if you get the dot product between I hat and another I hat, their magnitudes are equal to 1. So you have 1 times 1 times the angle between them, which is 0. Cosine of 0 is equal to 1. So the dot product is equal to 1. So here we see that the dot product of a unit vector with itself is equal to 1. What about for the case of unlike unit vectors, just like I hat dot j hat? The angle between these unit vectors is equal to 90 degrees. Cosine of 90 degrees is equal to 0. So we take note again that unit vectors are mutually perpendicular to each other. The angle between them is 90 degrees. So if we get the dot product of two unit vectors that are not similar, the dot product is automatically equal to 0. So I summarize these results in this table. Again, the dot product of a unit vector with itself is equal to 1. The dot product of unlike unit vectors is equal to 0. There's a simple way for us to write this. If we let E sub I be a unit vector, then the dot product between two unit vectors, E sub I and E sub j, could either be 1 or 0, depending on whether I is equal to j or I is not equal to j. This is actually the property of the Kronecker delta function. Let us consider the following example. Work is defined as the dot product of force vector and displacement. Suppose you pull a box with a rope at an angle of 20 degrees from the horizontal. So this is 20 degrees with respect to the horizontal. How much work did you do? When the box moves a certain distance, say 2 meters according to this problem, and the direction of motion is horizontal. So I draw here a diagram to help us visualize the problem. There's a box on the floor, and you pull the box with a force equal to F at an angle of 20 degrees with respect to the horizontal, and the box moves at a distance of 2 meters. Now, I forgot to specify the magnitude of the force here, so I now put it on the screen. So we let the magnitude of the force be equal to 30 newtons. So to get the work done, we simply need to get the dot product of the force vector and the displacement, that is equal to Fd cosine theta. Substituting the values, we find that work is equal to 56.4 Newton meters or 56.4 joules. Let us now proceed to the algebraic definition of the dot product. So recall that vectors such as vector A can be written in terms of its components. So the components of vector A are ax I hat, ay j hat, and az k hat. The same can be done for the case of another vector such as vector B given by this equation. So to get the dot product of the two vectors A and B, we simply write them in terms of their component forms as shown on the screen. Then we simplify or we evaluate the equation. We distribute the first term, which is ax I hat, to the terms of the second vector, and we get these terms shown on the screen. We do the same for the second term and also for the third term. In this equation, so on on the last term that I have just written, I've made a mistake. You have seen that it should be a sub y j hat, not a sub z k hat. I will correct that later on. Then after that, we we can simplify this further. So you see that the first term, which is ax I hat, that bx I hat can be written as ax bx times the dot product of I hat with itself. And you already know that that is equal to 1. So for other terms, you see that there are dot products of unlike unit vectors. And you know already that the dot product of unlike unit vectors is equal to 0. So some terms here will be cancelled. I will continue writing the other terms. And as I've mentioned earlier, there's a mistake here, so I am correcting it now. So the term that I am writing should be AY BZ. So I will just continue writing the other terms. All right. So we take note that the dot product of two unit vectors is equal to the Kronecker delta, ij. It could be 0 or 1 depending on whether I is equal to j or not. So you could see that we can cancel many terms here. While for other terms, the dot product of a unit vector with itself is equal to 1. The result is quite simple. You see that we are just looking at the sum of the products of the same components. Now, we can write this in a very simple way using the Riemann sum notation as shown on the screen. So that is the algebraic definition of the dot product. For example, find the scalar product of two vectors. Vector A is equal to I hat plus 2j hat plus 3k hat, while vector B is 4I hat plus 5j hat plus 6k hat. So the dot product is simply the summation of the product of the similar components of the two vectors. We just substitute the values for ax, ay, az, and bx, by, bz. The final answer here is 32. Again, because this is a scalar product, it doesn't have direction. Now let us consider the same vectors a and b. So now that we know the dot product, we can actually use the geometric interpretation or the geometric definition of the dot product to find the angle between the two vectors. So we take note that the geometric definition of the dot product of A and B is equal to AB times cosine theta. While the algebraic definition is that the dot product of A and B is the following: AX BX plus AY BY plus AZ BZ. So we can equate these two equations. We can write AB cosine theta equal to AX BX plus AY BY plus AZ BZ. So the angle theta is the angle that we are looking for. This is the angle between the two vectors A and B. So what we do is we divide both sides of the equation by AB. So we are left with cosine theta equal to the sum of these three terms divided by AB. So we take note that A and B are the magnitudes of vectors A and B. And how do we find the magnitudes of these vectors? We use the Pythagorean theorem as I have mentioned earlier. So the magnitude of vector A is equal to the square root of the sum of the squares of the components. The same is true for the case of the magnitude of B. So what we do next is we substitute these magnitudes of A and B in our equation. So the numerator is the same. Then for the denominator, we just write the square root of the sum of the squares of the components for the two vectors. And we just multiply them. And finally, to get angle theta, we simply get the arc cosine of the term on the right. So what I'm doing now is I am substituting the values of ax, bx, ay, by, and az, bz in our equation. So using your calculator, you should find the value of the angle, which is 12.9 degrees. So that is how you can find the angle between two vectors A and B. The next example that I will show you is an important application of scalar product. There's a relatively difficult problem in mathematics or in physics that is shown by this example. What is the angle between two diagonals of adjacent faces of a cube? To visualize this problem, I draw the x, y, and z axis. So I put one corner of a cube at the origin, and the cube is at the positive octant. So imagine the diagonal of two adjacent faces of the cube. For simplicity, I have chosen the faces at the YZ plane and the XY plane. So what I do is I let the length of one side be equal to 1, and the coordinate of the two corners of the cube that we are interested with are 0, 1, 1 and 1, 1, 0. So we let the diagonals be vectors A and B, and the angle between them is angle theta, which is what we're looking for. So using the coordinate, you can write the components of the vectors this way. So vector A is equal to j hat plus k hat, and vector B is equal to I hat plus j hat. Recall from the previous example that the value of the angle between the two vectors, theta, is simply equal to arc cosine of ax bx plus ay by plus az bz divided by the magnitudes of vectors a and b, or the product of the magnitudes of a and b. What we do next is we simply substitute the values of the x, y, and z components of vectors a and b. Using your calculator, you'll find that the value of the angle is equal to 60 degrees. So we see that the angle between these two diagonals is equal to 60 degrees. The second part of this video tutorial is how to get the vector product or the cross product of two vectors A and B. So suppose we multiply two vectors A and B. The result is another vector. That is what we call vector product. And the symbol that we use here is a cross, as you have seen. That is why this is called a cross product as well. Let us start with the geometric definition of the cross product, just like what we did for the case of the dot product. If we multiply two vectors, A and B, take note that vector A has a component that is perpendicular to vector B. Remember that for the case of the dot product, what we did is we multiplied the components of the vectors that are parallel to each other. For the case of the dot product, what we multiply are the vector or are the components of the vectors that are perpendicular to each other. So for this case, the magnitude of the cross product of A and B is as follows. It is equal to the magnitude of A times the magnitude of B times sine theta. So if you compare that to the definition of the dot product, it is different because in the dot product, we have used cosine theta. Now let us consider different cases for the values of theta. When A and B are parallel to each other, the angle between vectors A and B is equal to 0. So sine 0 is equal to 0. So if the vector product of the two vectors is equal to 0, you know immediately that they are parallel to each other. On the other hand, when vectors A and B are perpendicular to each other, the angle between them is 90 degrees. Sine of 90 degrees is equal to 1. Therefore, the magnitude of the cross product of A and B is equal to the product of their magnitudes, A and B. Now, this is the geometric definition of the magnitude of the cross product. Remember that if we have a parallelogram, we can find the area of the parallelogram by multiplying or getting the product of the altitude of the parallelogram and its base. So if you compare that to the figure that I have shown earlier, this is actually similar to multiplying the component of vector A that is perpendicular to vector B. So here we see that the magnitude of the cross product of A and B is actually the area of a parallelogram bound by vectors A and B. Again, this is the geometric interpretation or geometric definition of the magnitude of the cross product of A and B. So far, we have just talked about the magnitude of the cross product. Like what I have mentioned earlier, for the case of the vector product, the product has a direction. It is also a vector quantity. So let us see how we define the direction of the cross product. So suppose we get the cross product of vectors A and B. The angle between them is theta. The direction of their cross product, which is C, is perpendicular to the plane of vectors A and B, as shown in this figure. So take note that there are two possible directions that are perpendicular to vectors A and B. So it can either be upward or downward. So the correct direction is given by the right-hand rule. So what you do is you point your fingers to the direction of the first vector, which is A. Then you curl it towards the direction of the second vector, vector B. The direction of your thumb is the direction of the cross product For this case, it is vector C. So in getting the direction of the cross product, the arrangement of the vectors is important. So the cross product of A and B is equal to C. Now if you reverse that, cross product of B and A, that is actually the direction is opposite to vector C. So the order is important. Let us have an example. Find the area of a parallelogram bound by vectors A equal to 2 meters 30 degrees and vector B equal to 6 meters horizontal. Okay, so I draw here a two-dimensional Cartesian plane. This is vector A, the direction is 30 degrees, and there's also vector B, the direction is horizontal. So based on the geometric definition of the magnitude of the cross product that I have discussed earlier, it is equal to the area of a parallelogram. So the area that is shaded in this figure is simply the magnitude of the cross product of A and B. If you substitute the values, the area is equal to 6 meters squared. What about the cross product of unit vectors? Again, the unit vectors are I hat, j hat, and k hat. And let us first recall that I hat is directed towards positive x-axis, j hat towards positive y, and k hat is directed towards positive z-axis. Let us first find the cross product of I hat with itself. So the magnitudes are 1. So you have 1 times 1 times sine of the angle between them, which is 0. So the cross product is equal to 0. If we do that to the other cases wherein the unit vectors are similar, such as j hat cross j hat and k hat cross k hat, the answer is also equal to 0. Therefore, for similar unit vectors, the cross product of a unit vector with itself is equal to 0. On the other hand, let us consider this case. Cross product of I hat and j hat. Magnitudes are 1 times sine theta. So that is equal to 1. But again, there should be a direction, right? So the direction is given by the right-hand rule. It must be k hat. So there's a mnemonic device that I would like to teach you for you to easily remember the cross product of unit vectors. So you just write I hat, j hat, and k hat this way, and take note of the direction of rotation. If it is clockwise, positive, counterclockwise, negative. So if you write I hat, j hat, k hat in the pattern that I do on the screen, the result is positive. On the other hand, if you follow the second mnemonic device, you see that the result is negative. So in this mnemonic device, you simply have to follow the arrangement of the unit vectors. So again, the geometric definition of the magnitude of the vector product is that it is equal to the area of a parallelogram. What about the algebraic definition of vector product? So we again write two vectors, A and B, in terms of their components. Let us get the cross product of vectors A and B. Just like what we did for the case of that product, we simply distribute each term to the other term. In algebra, you call this the smile method. So you have axi hat cross bxi hat plus axi hat plus byj hat and so on. So I am now distributing the second term ayj hat to the terms of to the components of vector b. Then finally, we distribute the last term of which is az k hat to the components of vector b. We can then simplify each term. So the first term can be written as axbx times I hat cross I hat. Second term is axby times I hat cross j hat, and so on. And finally, the last term is az k hat cross k hat. So we again take note of the mnemonic device that I have taught you earlier. So using this, you can simplify this equation further. So I hat cross I hat is equal to j hat cross j hat, which is equal to k hat cross k hat, which is equal to 0. For the other terms, you use the mnemonic device. I hat cross j hat is equal to k hat, and so on. So we substitute the cross products of these unit vectors to the equation, and you see that some terms can be cancelled out. So what you can do is to rearrange the terms, and you can write it like this. So this is the final answer. You see that it is quite long and maybe intimidating for some, but we can neatly write this in a matrix form this way. The cross product of A and B is equal to this matrix. You write I hat, j hat, and k hat on the first row. On the second row, you write the components of vector A, and then in the third row, you write the components of vector B. Let us solve an example. Find the vector product of A and B such that vector A is equal to I hat minus 2j hat plus 3k hat, and vector B is equal to 4 I hat plus 5j hat minus 6k hat. So the cross product of vectors A and B is equal to this. We simply have, or we simply need to substitute the components of vectors A and B to the equation that we have derived earlier. We just do simple algebra, and you should be able to find that the cross product is equal to negative 3i hat plus 18j hat plus 13k hat. That is the final answer. This is the end of our video tutorial. I hope you enjoyed it. See you in the next video. Thank you for your attention.